Welcome to Tech Unpacked, where we explore the invisible engines driving our digital world. Ever been on a super fast journey only for it to abruptly stop and wait? That's exactly what your computer's brain, the CPU, tries to avoid every single microsecond. Today, we're looking at one of its most ingenious tricks: branch prediction. Imagine your CPU is following a recipe of instructions. It hits a step. If the mixture is too runny, then add flour, else continue stirring. This if statement is a conditional branch. Waiting to check the mixture's consistency would slow down the entire cooking process. So, what does a smart CPU do? It makes an educated guess. This is branch prediction. The CPU predicts whether the condition will be true or false. Will it need flour or just keep stirring? And it speculatively starts working on the instructions for that predicted path, even before it knows the actual outcome. If the guess is correct, awesome. Everything continues seamlessly. The CPU's instruction pipeline stays full, and your applications run fast. No stalls, no waiting. Now, why is this critical for something like, say, the smooth, crisp graphics you see on your phone or computer screen? This is where libraries like Skia come in. Skia is an open-source 2D graphics library used by many applications and web browsers to draw everything you see. Skia's code, like any complex software, is packed with these conditional branches, deciding how to draw a curve, what color to blend, or where to place text. Skia itself doesn't do branch prediction. That's a hardware feature of the CPU. But Skia's performance is massively boosted when the CPU can accurately predict the twists and turns in its code. So, how do these CPUs become such good fortune tellers? Early methods, known as static prediction, used fixed rules, like assuming a loop will continue. But modern CPUs use dynamic prediction. They learn from experience. A key component is the branch history table, or BHT. Think of it as a small notepad where the CPU jots down the recent outcomes of specific branches. Many use 2-bit saturating counters. This means if a branch usually goes left, a single incorrect guess won't immediately make the CPU start predicting right. It needs to be wrong twice in a row to change its strong belief, making the predictions more stable and accurate. Beyond just predicting taken or not taken, CPUs often use a branch target buffer, or BTB. If a branch is predicted as taken, meaning the flow changes, the BTB stores the actual memory address of where to jump next. This allows the CPU to start fetching instructions from the correct new location immediately, saving even more time. Some CPUs even employ hybrid or tournament predictors, which combine multiple prediction strategies and choose the one that's performing best for a particular situation. But what happens if the CPU guesses wrong? This is called a misprediction, and it's costly. All the speculative work done down that incorrect path has to be discarded, a pipeline flush. The CPU then has to restore its state and start fetching instructions from the correct path. This penalty can be tens of clock cycles, a significant hit to performance. That's why CPU designers pour so much effort into achieving prediction accuracies often well above 90%. This directly impacts libraries like Skia. Think of all the loops processing pixels or the conditional logic deciding how to apply visual effects. Each if statement is a branch. If these are frequently mispredicted, rendering slows down. Companies like Swan Tai, for example, actively work on optimizing Skia for specific CPU architectures, like RISC-V, by reducing the number of branches or realigning code to help the CPU's predictor make better guesses. While application developers using Skia don't directly control the CPU's branch predictor, understanding these principles helps in writing code that's more branch-friendly. Ultimately, efficient branch prediction is a cornerstone of high performance in graphics rendering and many other demanding computing tasks. It's one of those amazing, hidden complexities making our digital experiences fast and fluid. Thanks for tuning in.